Hello friends, welcome to my channel. In this video I will cover most important things from thermodynamics for Isro 2017 examination. This is part 2 of this video. Some important laws I will give you. First is Boyles Law. Boyles Law. Pressure is inversely proportional to volume. Temperature is constant. So from here P1 V1 equal to P2 V2, and in Charles' law volume is directly proportional to temperature. Here pressure is constant, so V1 by T1 equal to V2 by T2 according to Charles' law. Then Gasification law, Gay-Lussac's law. Here pressure is directly proportional to temperature, volume is constant, so P1 by T1 equal to P2 by T2. Then our general gas equation. In general gas equation, PV by T is constant. P1 V1 by T1 equal to P2 V2 by T2. This is very useful in solving the problem. So many times they asked problems based on this equation. Next is Joule's law. Internal energy is directly proportional to temperature. In Avogadro's law, a mole of a substance has a mass numerically equal to the molecular weight of the substance. For example, if you take 1 kg mole of oxygen, it has a mass of 32 kg. And if you will take 1 gram mole of oxygen, it has a mass of 32 gram. Avogadro's law statement is volume of a gram mole of all gases at the pressure of 760 mm Hg and temperature of 0 degrees Celsius is the same and is equal to 22.4 liters. Or in other words, you can say equal volume of all gases at same temperature and pressure contains equal number of molecules. So from here m equal to mass in kg, mu equal to molecular weight, and n equal to number of kg moles of the gas. So n equal to m by mu. M unit is kg and mu unit molecular weight unit is kg per kg mole. So m by mu, its unit is kg into mole. From here molar volume, this is useful in van der Waals equation. This question was asked in GATE examination also. V by N. Its unit is meter cube divided by kg mole. And V is total volume of the gas in meter cube. Next is our ideal gas, a gas which obeys the law PV equal to MRT. From here, R is characteristic gas constant. R equal to characteristic gas constant and Ru equal to universal gas constant, mu equal to molecular weight. One relation is here, R equal to Ru by mu. This is useful in solving problems. Sometimes they are not giving Ru value, so Ru value you have to remember. 8314 Newton into meter divided by kg into mole Kelvin. So in kilojoule it's 8.314 kilojoule per kg mole Kelvin. This is important, you have to remember this one. Universal gas constant value PV equal to MRT, or you can write it as PV equal to N RU, universal gas constant, into T. N is already discussed, number of moles, and N value is M by mu, mass by molecular weight. And Joule's law, one thing I forget to tell you, internal energy is proportional to time. Here internal is the function of temperature only for ideal gases. This is also important. Then Cp minus Cv equal to R, specific heat ratio Cp by Cv equal to gamma. So from these two equations, Cv equal to R by gamma minus 1 and Cp equal to gamma into R by gamma minus 1. Both unit is kilojoule per kg Kelvin. These four are useful in solving problems. So many times they asked. And gamma standard value, specific heat ratio. Specific heat ratio for monoatomic gas is 1.67. This is maximum value. And for diatomic gas or air, its value is 1.4, and for triatomic gas it's 1.33. These values also you have to remember. 2 times or 3 times they asked. Gamma minimum value is 1 and maximum value is 1.67 for monoatomic gases. Gamma depends only on the molecular structure of the gas, and then P1 V1 to the power gamma, P2 V2 to the power gamma, T2 by T1 equal to P2 by P1 whole to the power gamma minus 1 by gamma equal to V1 by V2 whole to the power gamma minus 1. This is very useful. So many times they asked these problems. And P2 by P1 equal to, in terms of density, rho 2 by rho 1 whole to the power gamma. T2 by T1 equal to rho 2 by rho 1 whole to the power gamma minus 1. Then polytropic process, PV to the power n equal to constant. In polytropic process, it's not adiabatic. This is very important, but it can be reversible. but it can be reversible. And one more thing is important. Gamma is specific heat ratio, property of the gas, but N is not a it's not a property of gas, and N depends on the process. One more thing is important here. P1 V1 to the power n, P2 V2 to the power n, 2 times asked in Isro examination, n equal to log P1 minus log P2 divided by log V2 minus log V1. In polytropic process, PV to the power n equal to constant. This is very important. Reversible adiabatic process, change in entropy equal to 0. And for reversible polytropic process, change in entropy it's not equal to 0. This is very important. This graph is very important for different values of n. Here n equal to 0 for constant pressure process, and for constant volume process m equal to plus or minus infinity. This one n equal to 0, isothermal process. Here pressure is constant, here volume is constant. Then n equal to gamma, where entropy is constant. Then our TS graph, temperature versus entropy graph. Both are important, PV diagram and TS diagram, for different values of n. Here, this is isothermal, n equal to 1, where temperature is constant, and here entropy is constant, n equal to gamma, S is constant. Here n equal to plus or minus infinity, V is constant. Here n value equal to 0, constant pressure process. This one constant pressure process, this one constant volume process. For different values of n. So many times, 3-4 times they asked questions from these two graphs. PV to the power n equal to constant and n equal to 0 for constant pressure process, and n equal to infinity for constant volume process, and n equal to 1 for isothermal process, and n equal to gamma for adiabatic process. For constant volume process, for heating and cooling, I will draw the PV and TS diagram. First PV diagram, then TS diagram. Constant volume process in heating, it will go like this. Initial state to final state. And in TS diagram, go like this. Constant volume process 1 to 2. and for cooling initial to final, and in TS plot 1 to 2. Both are important. For both other IES, GATE and Isro also this is very, very important. Next is for isobaric process or constant pressure process on heating or expansion. This is PV diagram, then TS diagram. In PV diagram, from initial state to final state, it will go like this. And in TS diagram, for heating and expansion, initial to final, pressure is constant. And for cooling and compression, PV diagram, then TS diagram, initial state to final state, it will go like this, initial to final. Next is for isothermal process, expansion. For expansion, isothermal expansion, PV diagram and TS diagram. Expansion will go like this, initial state to final state. Isothermal, so parallel to x-axis, initial to final. Then for compression process, isothermal compression, PV diagram and TS diagram I will draw. PV diagram and TS diagram. For compression, it will go like this, initial to final, same parallel to x-axis, 1 to 2, initial to final. 1 represents initial and 2 represents final state. Next is for isentropic process. For expansion, PV diagram and TS diagram. PV diagram, then TS diagram. For expansion, isentropic expansion. Initial to final, parallel to y-axis, initial to final. And for compression, isentropic compression, PV diagram and TS diagram. Initial to final. This is PV diagram, TS diagram, parallel to y-axis, initial to final. All four are important: constant pressure process, constant volume process, then isothermal process and isentropic process. Which property is increasing, which property is decreasing on expansion and compression, or heating or cooling, which one is increasing, and that graph how it will behave according. Sometimes they will ask the question based on these processes, so you have to remember all four processes. This is very, very important for IES, GATE and Isro also. Thank you friends. Thank you for watching my video. Thank you.